Okay, let's talk a little bit about linear transformations between vector spaces or linear maps. So you fix a field F throughout, take real numbers if you wish, and let's say V and W are two vector spaces over this field F. A function T from V to W is called a linear map, also called linear transformation. I'll just prefer this one because it's shorter. If T of V plus W is T of U plus V is T of U plus T of V for all U, V in V, then T of a scalar alpha times U is alpha times T of U for all U in V and all scalar alpha in F. And then a bijective linear map is called a isomorphism of vector spaces. You say two vector spaces are isomorphic if there is isomorphism from one to the other. And if the two vector spaces V and W are isomorphic, then you write it like this. So this is isomorphic. That's a notation. Just means that there is a isomorphism from V to W. Isomorphic vector spaces have the same properties, same vector space properties. Yeah. So example, if you wish. This is a linear transformation from R3 to R2, let's say. Okay. You give me a point in R3, X, Y, Z, and I give you a point in R2, this one. So 1, 2, 3, if you apply, you get 2 minus 6 plus 3, 1 minus 3, which is minus 1 minus 2. Stuff like that. That you can check satisfies these two properties. So it's a linear transformation. This linear transformation is given by a matrix. You can write down a matrix by looking at this formula in the obvious manner, so that applying this T is same as multiplying by this matrix. So this is same as T of X, Y, Z. So if you give me a linear transformation from R3 to R2, I can write down a 2 by 3 matrix such that left multiplying by that matrix is same as applying this linear map. And then composition of linear transformations correspond to multiplication of matrices. Okay, so the matrix algebra is nothing but composition of linear transformations. And in fact, every linear map between finite dimensional vector spaces can be represented in this way once you choose a basis for the domain and the codomain vector spaces. Yes, all this is standard stuff. I guess you're familiar from linear algebra, at least over real numbers, but it goes through without any change. Just want to mention a few little lemmas about linear maps. If you have a linear map phi from V to W, and you have a subset of V, let's say. So when you apply this linear map, what you get is linearly independent. Then the original thing was independent. If you take a bunch of vectors and you apply a linear map, and these guys are independent, then the original things must have been independent. And the reason is very straightforward. If the original things were dependent, then some non-trivial combination of these guys are 0. But then the same combination of those guys would also be 0, because when you apply the linear transformation, the sum can be broken up and the scalars can be taken out. So if you take a combination like this, alpha 1 v1 plus alpha n vn, and this is 0, then when you apply phi to it, you can first break the sum up and then move the scalars out, and you will get the same combination of the phi v's is also 0. Yeah, so that would say that those are also dependent. But B says that if B spans V and phi is onto, then the image of those vectors also span W. That's also very straightforward. I leave that as an exercise. And if you use that for an isomorphism, then you can apply it in two ways and then you get more. So if you have isomorphism, by isomorphism here I mean vector space isomorphism, so a linear isomorphism. Let phi from V to W be a linear isomorphism, and you have a subset of V. So if the B spans V, then phi B spans W, and vice versa. B is linearly independent if and only if phi B is linearly independent. B is a basis if and only if phi B is a basis. In particular, isomorphic vector spaces have the same dimension. Dimension, remember, is the size of a basis if they're finite dimensional. That follows immediately from the previous one. And then this third one is rather important. It tells you how to construct linear maps given a basis. Basically, it says that if I give you a basis of V, this is a basis of V, and if you want to give a linear map to W, all you need to do is choose arbitrary elements. And you are allowed to send B1, B2, Bn to arbitrary elements of the target vector space, and you get a unique linear map that does that. So you just need to tell me where the basis elements go, and then everything else is uniquely determined. Because there is no linear dependence between the basis elements, you are free to send the basis elements to whatever you please. And once you know where to send the basis elements, you also know where to send all linear combinations. Because if you send B1 to W1, B2 to W2, Bn to Wn, then you have to send this guy to the corresponding linear combination of the W's. But of course, every element of the vector space can be written as such a linear combination, so you know where to send them. So that's the uniqueness. So there is only one way to make this linear map. That's essentially the proof of this lemma, but it's very useful. It tells you that once you have a basis, defining a linear map is sort of trivial. You take arbitrary elements of the target vector space and send the basis elements to these. So next, we want to talk about this important theorem that when you have a linear map, then the dimension of the kernel plus the dimension of the image is equal to the dimension of the domain vector space. So we'll need some preparation for that. So we'll go